Okay. So we will welcome everybody again formally that we are doing this workshop on T-ray imaging and spectroscopy, and we have done the imaging part in the last 4 or 5 sessions. Today we start the T-ray spectroscopy or terahertz spectroscopy. And it will take probably 3-4 sessions, and then this workshop will end. Our goal is that at the end of the workshop, you please present some kind of a presentation on whatever is your interest. If you have data or not, probably will not have data in your hand, but that's okay. Some kind of either a review or proposal or that kind of thing. And at the end of the workshop, you all will get a certificate of attendance. So let me go to the presentation. Moment. And today we start. Can you see my screen? Oh, I haven't shared it yet. So let's share the screen. All right, so you see terahertz time domain spectroscopy. You have some background in this spectroscopy because there's such a common tool in the scientific research world. There are several different kinds of spectroscopy available, but we particularly talk about time domain spectroscopy. And this time domain is the key because here the measurements are done in the time domain. And then, of course, then we use the mathematical transformation to get to the frequency domain or wavelength or some other kind of variables in different spaces. So you'll see, we'll go through briefly. We're not going to go in details of any of the things, but high level principle, then the measurement and setup, time domain experiment, interferogram. There's a technique called pump probe technique that is utilized here. Then how we get the frequency domain spectrum, and deep level spectroscopy, which is slightly different than doing all the surface scale spectroscopy. And the biggest part in the spectroscopy is the interpretation of the spectrum that we generate. And that will be done in terms of some examples. So basically, this is, this cartoon on the upper right. Can you see the screen clearly, or is it hiding anything? Good. So the cartoon on the upper right is kind of universal. There are a lot of things happens, but I have summarized here only main things. When any energy is incident on an object, and the material you can think as a matrix of atoms or molecules. So when we have any energy incident on it, which in our case, the terahertz radiation or T-ray, then some of the radiation will be reflected back, some of the T-ray will transmit through, some of them will get scattered, and some of them will be absorbed. But there are many other, different kind of scattering, different kind of absorption, even reflection, partial transmission, etc., happens. But in general, this is the basis. So in spectroscopy, we measure either the reflected energy or the transmitted energy. In some cases, both. And when you measure the both, then transreflectance is the term that is used. So, but in either case, we get the information about the material or the sample that we are investigating. So the time domain is in other spectroscopy, such as, let's say, IR or Raman. What is done is either the reflected beam or the transmitted beam is incident on a grating, some kind of a grating. There are many different kinds of gratings, dispersion gratings. That dispersion grating splits the signal, incident signal on that grating into different wavelengths or frequencies. And then based on the sample, that frequency changes, or some cases there are resonances, and some cases there are no resonances, and so on and so forth. So that grating is the key for all kind of spectroscopy, except in this terahertz or T-ray spectroscopy, because instead of using a grating, here we have time domain signal. And I will explain to you in a minute, but we don't have any grating. I know that's a good thing and bad thing. It's a good thing that you don't need a grating. And there are the limitations of the gratings can be eliminated. The bad thing is that the grating is a accepted technology. People understand it very clearly. You get one or two peaks from that grating. Easy to explain what those peaks are for. In fact, other than terahertz, all other kind of spectroscopy, be it NMR, be it Raman or IR or UV or visible, or even microwave, all different kind of spectroscopy is mainly the response comes from the bond vibration. So if you have a molecule or an atom that has, some kind of a, let's say, molecule, then some other kind of substituent is added to the molecule by means of bond. And that bond is, sensitive to IR, NMR, et cetera. So based on that energy of that bond or frequency where it resonates, then we do all different kind of chemical interpretation, mostly. But, in a molecule, you have other resonances, other motions as well, not only bond, but there is a translational, rotational, torsional, and even translational. All those kind of resonances are there. And when a molecule, if you synthesize a molecule, for example, unless it goes to the low energy state, so there is a conformational problem as well. Stable conformation happens only at low energy state, but as you synthesize a molecule, it is not always the stable conformation. So that conformational difference creates some resonance as well. So all of those resonances are sensitive to T-ray. So that's why T-ray is the highest form of sensitive radiation compared to everything else out there. And that's the importance. On the other hand, the gratings are not effective for T-ray spectroscopy. So this, how do we then detect molecular events, so to speak? So the technique is called the pump probe technique. In this diagram on the left, as you can see, there is a pump beam and there is a probe beam. And the pump beam goes through an optical delay, actually a terahertz delay here, and then then that beam hits the terahertz emitter where terahertz is generated, and eventually the terahertz is then interacted with the probe beam. So this interaction of the pump and probe beam creates a signal, what we call an interferogram. And then eventually it goes, it probes a sample here, and this sample can be measured either in transmission or in reflection. So, this gives this gives the most sensitive way of probing our samples. And why is that important? Because if you consider even the water molecule, H2O, and this graph is taken from a textbook written by Griffiths and DeHassett in 2007, published by Wiley. It shows that even for this simple model, if you consider a potential energy diatomic molecule as a function of displacement during a vibration, one should get a lot of absorbance states, meaning that the water molecule is resonating at so many frequencies. Wave number is unit of a frequency. So many frequencies they're resonating. But if you put the water molecule in the FTIR machine or any other spectrometer, you may end up getting one or two peaks. You are not able to see all those peaks that are possible in that molecule. And why is that? Because of the sensitivity. Like I explained, it's only the bond vibration that is sensitive to those wavelengths, probing wavelengths, but not others. So that's why there's a need for higher sensitivity, because we want to understand the molecule a lot better than we can with other techniques. So then, how do you know that if you build a spectrometer with this T-ray, first of all, there's a need for calibration. How do you know that your spectrometer is giving you what you are looking at? So, we had built this spectrometer and then calibrated with respect to known samples that have been published. And here is a data from the NIST on water vapor molecule, or water vapor as water as molecule, but in vapor form. And we got the spectrum blue is from liquid water. So it's spread it out as opposed to very sharp line because of this liquid water formation. This is another way of showing the experimental setup. The diagram you saw before, this is where the sample is mounted, and then there's a transmission and reflection detectors that you can choose. It's all in the software. You can choose either the transmission or the reflection, depending on the sample that you are working on. And then sample consideration can be solid, liquid, or even gaseous sample can be done with this setup. Solid samples you can mount directly. Many solids are dissolved and formed into film on a substrate, and then the substrate is mounted and spectrum is taken. For liquid samples, you can use different kind of qubits. Gaseous sample may be measured either stationary or under flowing conditions, but gaseous sample would need a special sample holder, meaning that leak proof. So there has to be a gas in and gas out. That's how you can put the gas in there and do the spectrum. And reflection and transmission measurements can be done, or both should be done, depends on the situation. And then in spectroscopy, reflection, transmission, standoff distance, etc. Those are the experimental details that an experimentalist can choose. And then measurement can be done, reflection, transmission, or transreflectance. Either one parameter or multi-parameter measurements can be done, and etc. So again, the general procedure is, this is just the user manual repetition here. Is mount the sample, acquire spectrum, then the Fourier transform, and analyzing the sample. All of these softwares are built in the machine, so everything is given. So again, this cartoon you saw before, but in analysis, when we talk about Fourier transform, the Fourier transform is not a simple one equation transform. It's not one single thing anymore. The Fourier transform has a lot of different aspects, and mathematically they have been worked out for over the many decades for different situations. So fortunately, we have all of them, or most of them. There may be something that we don't know, but as you know, all of them are known things are in the software that comes with the spectrometer. Those are the Fourier spectrum, meaning that simple Fourier transform is done. Then Fourier transform with a data window. So you can window, the software gives a lot of options. Most commonly we use is that Fourier spectrum of unevenly sampled data, meaning that when you do the experimental measurement or data acquisition, all data are not equidistant distance in time, but that's a requirement for regular Fourier transform. The original Fourier transform requires that data should be in equal intervals, but experimental data are anything like that. So then there is an option, and this is actually worked out by scientists from NASA, because when they were collecting the extraterrestrial data, that was never equidistant. Therefore, they came up with this particular algorithm, in which case they create equidistant points and then apply the Fourier equation. But we also have autoregressive transformation, and then also moving average transformation, ARMA, that is autoregressive moving average. And then Fourier spectrum is also a very special kind of Fourier transform, minimum variance spectrum or transform. Eigenanalysis. This is another important, we have used a lot, it's called eigenanalysis Fourier transform. What it does is that, and I will show you the examples as I go, terahertz, because it is so sensitive, it gives you a whole bunch of peaks, absorbance peaks, or some other kind of space, but a lot of peaks. And it becomes almost impossible to explain all the peaks because they are not a lot of them are not known. So this eigenanalysis transformation, what it does is it reduces the peaks to only that fits the eigenvalue of that system. This is very, very useful. So let's say, just to give you a crude example over here, let's say I have a pharmaceutical, ingredient, API, active pharmaceutical ingredient, and I'm formulating some kind of tablet or pill or whatever, and I want to know if this API is present there or not. Then this eigenanalysis, what it does, once we know the peak value corresponding to the active API, the pure form, then in that formulation, either tablet or something, if we see the same peak, then we can identify. It's almost like Raman signature, but in a different way. So eigenanalysis transformation is very, very useful. And the other is a short time Fourier transform, which is different than regular Fourier transform. Why? Because in Fourier transform, if you can imagine that, it converts the time domain data into frequency domain data, right? So in doing so, what it does, it loses the time values, gives you the frequency domain results. So the question is, how do we know at what time, at what frequency? Sometimes that question comes up. And if that comes up, then we can use this short time Fourier transform. It does preserve the time axis as well. So you get three-dimensional plot for both time and frequency. So that's sometimes very useful. And the same idea is wavelet transform. The wavelet transform does very same thing, but it defines wavelet before doing the three-dimensional transformation. Then, variation of the wavelet transformations. As you can see, as a scientist, when we want to study something really, really carefully and know everything about it, we have the suite of software to study spectroscopically. So it's a little bit absorbed, but you can make it simple by doing either the Prony analysis or eigenanalysis, and then you can do the, all the details as I will show you in the examples going forward. Oh, I already have shown you this one. There's more of the comparison with the T-ray spectrum and the water spectrum that has been reported. So make sure that we're getting the right thing. There is some differences in these peaks. That's because of the experimental conditions. But the whole water spectrum, we wanted. The other thing, one other important thing is that we have here the spectrum from 1 wave number to 1,000 wave number. So this is the distinction. If you do the IR or FTIR, you get about from lowest end, maybe 400-500 wave number to 4,000 or so wave number. So that's high frequency area, and that's where the bond vibration comes in. But as you can imagine, molecule as a whole is much heavier than just the electron bond. Therefore, the heavier region is low frequency. Molecular response is in the low frequency region, and that's what we capture with T-ray. So one of the basic distinction with T-ray spectroscopy with other kind of spectroscopy is that we are in the low, very low frequency region that cannot be accessed by some of the other techniques. So it's an important distinction, but this is where we get a lot of important signature of the molecule as a whole. So another calibration is, again, this is polyethylene spectrum, which is a common window material that is used for FTIR and that kind of spectroscopy. So polyethylenes have known spectrum, and therefore when we do the characterization, we eliminate the polyethylene peak, and all other peaks then become important, and we go on explaining them. So what we do is with terahertz, as you can see, these are the known peaks from polyethylene from other experiments. These are the known ones. And so we want to show you that if we can reproduce those peaks that have been reported already. And the answer is yes, we can reproduce those peaks that have been reported in the literature. But nonetheless, we also produce more peaks. They're very reasonably, looking more peaks that we have gotten from T-ray that other technique kind of missed. So it may be a controversy, but it may be an opportunity. So it depends on the situation. If we can explain these peaks for whatever the science they are telling us, then this is a good thing. If we can't explain, then we produce kind of, controversy. But nonetheless, the instrument gives us the opportunity to create those peaks that otherwise was not produced. After here, if you have any question, then probably we can take it from here next time, or we can go to some specific examples. Spectroscopy is a really absorbed area, pretty complicated area, but also it produces the most, a lot of important information that we have been able to, this spectroscopy started long time ago, including Nobel Prizes that were given. I think Rahman got Nobel Prize for the Raman effect. What it means that there's a shift in frequency or in wavelength. Meaning that if you have a gold substrate, for example, a pure gold substrate, right, then it will get its resonance absorbance peak. But now on that gold, if you absorb some molecule, then there's a shift of that peak. Therefore, if you can measure that shift, you can identify that molecule. That's the basic principle. So, that, starting from there have been a lot of different kind of spectroscopy. It became a tool for material or drug or that kind of identification. So it's important that we can use this for our benefit. So if you guys want to ask any question at this point, anything to clarify, I know a little bit too much in one day, but feel free to, ask any question.
This is after the pump. This is a probe signal. These are all probed signals?
No. So it's not all probe, because what happens is, so interferogram, this signal, as we call it.
Okay, yeah, okay.
But still, this is a very important question that you asked. I'm glad that. So this is what we call an interferogram, right? In interferogram, you see the reflected or transmitted signal on this y-axis, but the x-axis is time. This is the only spectroscopy that you will see the x-axis as time. So this is a time domain evolution of the interaction of the pump and the probe beam. So it's not everywhere the interaction is there. And why we have a peak when in time domain, we have the resonance. We have the, things are responding. So in the beginning is kind of nothing happening, but then there is an interferogram. So the whole curve is count versus the time. And as we have measured only over 6 picosecond or so, 6.5 or so, that kind of. So 5, 6, 7, maximum 10 picosecond measurement. And that produces that, the frequency spectrum over 1200 wave number, or up to 30 terahertz. This can be converted into terahertz. That will be about 30 or 32 or so terahertz. So This interferogram is the basis of the measurement, and that
And every signal or spectra after this slide was after the Fourier transform. So the next slide was also after the Fourier transform of the time domain.
oh yeah, this is the frequency domain now.
Yeah.
So this signal, this time domain. See the empty,
Yeah.
the red curve is the empty signal. There's no PE card. There's no PE card there yet. So once you put the PE card, then because of the PE card is producing some, not all the signals is like open. So therefore the peak is a lot shallow compared to the empty cell. And then this blue one is Fourier transformed into the frequency domain. So yeah, this frequency is the same, frequency domain signal is the same as this one. It's just truncated to up to 700 wave number because of that comparison. This is what is available in the literature, the red curve. And there's a reference here, as you can see. So that's why we truncated at 700. Above 700, this signal, this peaks that we have computed from here, except we couldn't compare them. But then these ones are comparable. So this is 723, 722 and a half, etc., etc. Within the experimental error limit, they are close to each other.
How is a scientist to know that this is not a Raman spectrum?
So Raman spectrum is by itself is not a spectrum. Raman shift is more important. So if you take an FTIR spectrum, for example, and then do the Raman shift, still on the same instrument, you still can get. So in fact, with T-ray, we have T-ray Raman spectrum as well. So Raman is a phenomenon of shifting the frequency for some molecule or some material, right? So when we do in the T-ray region, we call it T-ray Raman. And I will show you those examples as well, how we do the T-ray Raman. So Raman is an effect. Raman effect can be utilized in all different kind of spectrometers as well. Except probably NMR has its own shift. So NMR has a fixed signal. Therefore, with respect to that fixed signal, every material will show characteristic shift. So in that case, that is the NMR signal. But in case of FTIR and that kind of spectroscopy, visible Raman can be manifested that way by shifting the peak. I probably will have some example. So that's a very good point. Any other point? Okay, so we'll repeat it again a little bit next time, but I have an example here for you, which is what we call is the endohedral system. Why endohedral? Because this is a buckyball, and what the chemists found a way that it's a soccer ball like thing, right? It's a big molecule, C60, or even there is C70, etc. But this is a particular sample of C60. So they opened up the cage, they call it cage, and then they open the cage by some nifty chemical reaction, and then they insert the hydrogen in that molecule, and then they close the cage. So now hydrogen molecule is inside the cage of the buckyball or fullerene, loses its translational motion, but still have the rotational motion. So this is a, there are ortho and para. Both of them have different kind of signal. So some chemistry is very, this work was actually, this sample was prepared by collaboration with American and Japanese scientists. I have a reference here. But before I go to that references, as you can see, because C60 is such a huge molecule, it has many different kind of resonances. And because of those resonances, you can generate different kind of absorbance peaks in their spectrum. And this group at Arizona State University has actually done a lot of work on this buckyball spectroscopy. And they have reported, so we found their references, and they have reported that this kind of, at this frequency, in other words, wave numbers, you have those motions corresponds to this kind of wave numbers. So it's a huge work that they have done. We were fortunate to get their references. And then we tried, the problem came is that when they synthesized this molecule, this particular molecule, what is called endohedral fullerene, endohedral because the hydrogen has been, put in the cage of the C60 molecule. And there's another sample that deuterium was also kept in there. That's why it is endohedral. When they synthesized this molecule, and they did run, the Japanese group published this paper. They did FTIR, and for all practical purposes, they couldn't see any difference between the pure C60 and endohedral C60, or they call H2 at C60, meaning that hydrogen molecule inside the C60 cage. So it's the same spectrum. And the NMR also was not able to discern much. So I was fortunate to, this work was done by my advisor who passed away now with the collaboration of the Japanese team. So Professor Nicholas J. Turo, who in his time, he was the highest published chemist all over the world, and he also wrote books on photochemistry. He's known for his work in photochemistry. So I was his postdoc for several years. So I was fortunate to be in touch with him, and he said, "Anis, can you look at this?" He has a huge lab at Columbia University, and NMR is their main instrument. They do a lot of other things among the NMR, which is a big focus there. So even with NMR, these two molecules looked not much different. So we had some sample from Nick, his lab. Then we did the terahertz spectroscopy. So as you can see, the blue is the C60. The red interferogram is the H2 at C60. And then the green one is the D2 at C60. Now, as you know, deuterium is heavier than hydrogen. So we expect the spectra will be different. And then we enumerated those observed peaks with the peaks that I showed you before. Those are published by these authors, Menendez and Page at Arizona State University. Here are the references. I think these works are, they are available on the internet as well. This is a vibrational spectroscopy of C60. The other paper is the vibrational modes of Buckminster Fullerene C60. So bottom line is that they found the lowest frequency peak at 272. And we have one very close to that at 271, but in the low frequency region, we have this peak, 6.44 to 19, etc., that the T-ray has been able to generate. And as you can see, buckyball being a heavy molecule, we anticipate to see the low frequency vibrational absorbance states. So that's what they are, but only this one matches closely within the experimental error, of course, to their work. In this group, we have two close match, 343, 353. We have 341 and 361, which is as close as it can get. Everything else is different. Here we have more match, etc., etc. Some places we don't have a lot of match. So nonetheless, point is that the instrument of the terahertz time domain spectroscopy is now a tool that we can use to check out all of these things. And so we have more examples. For example, non-ionic detergents. These are used in biopharmaceutical manufacturing. This was a collaboration with, used to be as part of NCI, not now they became a different company, Lidus Biomedical, but these are the, there's a name for this, I forget right now. It's called, I forgot it. I'll remember and I'll let you know later, right? So the point here is that if you do this, this one has 9 to 10 carbon, and this one has 9 carbon. So this C9H19 and C8H17. So these two molecules are very close. And because of they're so close, IR is not discerning. You get the same basic peak between those two molecules. So then how do we know which one is what? And that's where we work with them. And in T-ray spectrum, up to 20 terahertz here, this is in not wave number, but T-ray, it's called Triton, right? Tergitol, sorry, this is called Tergitol, yeah. So this one is called Tergitol, and this one is called Triton. So with T-ray, then you can see very clear distinction between those two closely spaced molecules, and so on and so forth. Let's start from here next time. This is a oligonucleotides, which is more of Yukta's world probably, but we'll go from there. So this talks about the single nucleotide polymorphism in the DNA, and we'll come to that next time. All right, so let's stop here for now. And if you want to discuss anything else, or again, what we have discussed today, comments and questions are welcome. Okay. All right. So we'll
Thank you very much.
Sure. We'll pick up from here next Friday, the same time. All right.
Thank you.
Thank you, Uncle. Thank you.
Okay. Wonderful. Have a good weekend.
You too.
Bye now.